Before an earthquake shakes the ground, something sneaky might happen first. A slow, quiet movement with no shaking at all. No one is aware that right under their feet, the land is preparing to tremble violently, wreaking havoc, bringing destruction and devastation. A new study shows that such a slow creep might be how earthquakes begin. To figure this out, scientists didn't start with giant pieces of the earth. Instead, they went into a lab and used clear plastic sheets called plexiglass. They pushed two sheets of plexiglass sideways against each other, just like how tectonic plates, huge chunks of Earth's crust, push against each other underground. As they pushed, the plastic cracked, kind of like what the Earth does during an earthquake. And even though it was plastic and not rock, the physics, the way things break and move, was the same. Earthquakes happen when two tectonic plates try to slide past each other, but they get stuck. The edges between them don't move easily because of something called friction. It's kind of like when your shoes grip the ground. Over time, the plates keep trying to move and stress builds up. Think of it like bending a stick. At first, it doesn't break, but if you keep pushing, it will eventually snap. The spot where the plates are stuck is called a fault, and there's a thin, brittle part in that fault. By brittle, I mean that it doesn't bend, it just breaks. Here's how it happens. First, a tiny crack forms. It's small and moves slowly. There's no shaking yet, but something is already happening under the surface. The crack spreads, building up more energy. When it finally reaches the edge of the brittle zone, boom! It speeds up, suddenly racing forward really fast, almost as fast as sound. And that's when the Earth starts to shake. So scientists decided to find out how that very first crack starts. They conducted their experiment, whose setup was similar to a type of fault in the real world called a strike-slip fault, like the San Andreas Fault in California. Even though the materials, plastic versus rock, are different, the way cracks form and move is exactly the same. The experiment has helped scientists understand that earthquakes don't always start suddenly. Sometimes there's a slow, quiet start, like a warning sign before the big quake. This early stage of an earthquake is called a nucleation front. It's like a seed of a crack, gently creeping through the material long before any actual rupture happens. This quiet and slow movement doesn't release energy into the surroundings. At first, scientists thought of cracks as simple one-dimensional lines, like a straight tear in paper. But something didn't add up. The slow-moving nucleation front wasn't behaving like a normal, fast-moving crack, and it wasn't clear why or how it suddenly sped up and became an earthquake. The answer came when scientists realized they had to think in two dimensions instead of one. Instead of imagining the crack as just a fine line, they began to think of it as a patch, like a growing circle, that starts at the surface where two materials touch. As this patch spreads out, more material along its edge has to break. The important thing here is that the energy needed to break the material is related to how long the patch's edge or perimeter becomes. The bigger the perimeter, the more energy it takes to keep breaking. That's why this patch moves slowly at first. It doesn't yet cause the violent shaking we associate with an earthquake. Because it moves without sending shaking waves, this stage is called aseismic. Eventually, the growing crack patch spreads beyond the special brittle zone, where the materials are stuck. Outside this zone, the energy needed to keep breaking the material doesn't increase anymore. Instead, there's now extra energy building up, more than what's needed to keep the crack growing slowly. This extra energy doesn't stay quiet. It suddenly powers the crack to move much faster, turning it into a full-speed rupture. That's the moment when the earthquake begins and the ground starts to shake. These findings help explain how earthquakes might start off slow and silent before quickly turning dangerous. They show that small, slow cracks can suddenly transform into powerful, fast-moving ruptures if the conditions are right. Scientists believe that they can learn to detect the aseismic stage before a crack speeds up. It might one day be possible to predict earthquakes, or at least understand the warning signs better. Now, even though earthquakes are only the third most common type of natural disaster, they cause the highest number of fatalities. NASA plays an important role in studying earthquakes by using satellites that orbit the Earth. These satellites collect data and images that show how the ground changes after an earthquake. For example, they can detect when the land shifts, rises, sinks, or cracks. These surface changes help scientists learn more about the strength and impact of earthquakes. NASA's satellites can also track changes in nighttime lights. If a city goes dark after a quake, that's a clear sign that the area may have lost power and could need help. Now, how about we talk about the most common earthquake myths, like the one about megaquakes? Some people really worry about super huge earthquakes, but there's a limit to how big they can get. The size of an earthquake depends on the size of the fault where it happens. A longer and deeper fault can cause a bigger earthquake. For example, the San Andreas Fault in California is long, about 800 miles, but not very deep, around 10 to 12 miles. This makes earthquakes bigger than magnitude 8.3 on that fault very unlikely. The biggest earthquake ever recorded happened in Chile in 1960. It had a magnitude of 9.5 and occurred on a huge fault that was almost 1,000 miles long and 150 miles wide. Technically, there's no set limit on the magnitude scale, but an earthquake bigger than magnitude 12 would need a fault larger than Earth, which just isn't possible. Now, earthquakes can happen near the surface or deep underground. Most occur in Earth's crust or upper mantle, down to about 500 miles deep. But the deepest ones happen only at subduction zones, places where one part of Earth's crust slides under another. In California, almost all earthquakes happen in the top 15 miles of the crust. One exception is the Cascadia subduction zone in Northern California, which continues up through Oregon, Washington, and Canada. Another misconception is that the ground can open during an earthquake, but usually that only happens in movies. A giant crack opening and swallowing things up during an earthquake is just fiction. In real life, the ground on either side of a fault slides past each other. It doesn't pull apart or open wide. Small cracks or holes can happen during landslides or ground failures, but not along the actual fault line itself. Faults don't open up because if they did, there'd be no friction, and without friction, there wouldn't be an earthquake at all. Now, some people think California could break off and sink into the ocean during an earthquake, but that's not how it happens. The ocean floor is just lower land with water above it. California can't fall in. What's really happening is that southwestern California is slowly sliding north toward Alaska along the San Andreas Fault. The Pacific Plate, which California sits on, is moving about 2 inches per year, about as fast as your fingernails grow. So, in about 15 million years, Los Angeles and San Francisco could be neighbors. And in 70 million years, Los Angeles might be sitting near Alaska. I can't wait. People often wonder whether an aftershock can be bigger than the earthquake itself. Aftershocks are smaller earthquakes that happen in the same area after a larger one. They're like our planet's way of settling down after the main shock. But if an aftershock turns out to be bigger than the first earthquake, then we call the bigger one the main shock, and the earlier one becomes a foreshock. About 5 to 10% of earthquakes in California are followed by a stronger one within a week. It's also possible for two quakes in the same area to be about the same size. However, very large earthquakes are rare, so it's even rarer to see two huge ones happen close together. It was in the year 2014 when a satellite snapped a picture of something unusual in the middle of the Pacific Ocean. It was a giant, almost perfect ring floating all by itself. It was an eerie sight. This formation showed up thousands of miles southwest of Hawaii and was about 280 miles wide. Who created this ring? How did it appear there? The questions were countless. The huge ring was spotted by NASA's Terra satellite with the help of a special camera called MODIS. Later, after examining the images, scientists realized that the ring was made out of perfectly shaped clouds. Even though clouds like this aren't super rare, it's not common to see one that big and completely on its own. Normally, such clouds show up in groups, not just hanging out solo in the middle of nowhere. The ring is made of puffy cumulus clouds. It turned out that it had been shaped by something called a Rayleigh-Bernard convection cell. It's a fancy schmancy way of saying that the clouds formed when warm air rose and cooler air sank, creating a circular pattern. Now, there are two types of such cloud cells. One is a closed cell, where cold air sinks around the edges and clouds pop up in the middle. The other is an open cell, where cold air sinks in the center and clouds form around the outside. And that giant ring floating over the ocean was exactly a closed cell, hence its cool shape. Interestingly, such cloud patterns usually look like a bunch of hexagons packed together, like a beehive in the sky. But this one was out there all by itself, which made it even more eye-catching. Now let's take a look at how the ring's formation happened in detail, shall we? At one point, the sun heated up the water or land, warming the air above it. That warm air got lighter and started rising. Cumulus clouds formed. Maybe it even rained a bit. When that rain came down, it cooled the air beneath the clouds. That cooler air then sank and spread out in all directions. But when it ran into the surrounding warmer air, it pushed the warm air upward again. That's how the ring of clouds formed around the original spot. This whole thing happened just south of the Intertropical Convergence Zone, a region near the equator where trade winds meet and often cause thunderstorms and heavy rain. That particular location probably helped with the formation of this cool cloud pattern too. Now, take a look at the right side of the satellite image. The ocean looks super shiny there, almost like silver. That shiny effect is called sun glint. It happens when sunlight reflects directly off the ocean's surface and hits a satellite camera just right. It kind of turns the sea into a ginormous swirling mirror. The cool thing is that the texture of the water, whether it's smooth or choppy, changes how that sun glint looks. Most of the time, the wind stirs up the surface, creating waves. These waves normally scatter the sunlight in different directions. But some of that light still hits the satellite, so the area looks shiny. But sometimes, if the water is super calm or there's a break in the wave pattern, it can create darker patches where less light gets reflected back. It gives sun glint zones a strange, patchy look. So if you notice really dark spots in satellite images, keep in mind that they might not be shadows or oil spills. Most likely, they're just signs of how the wind and waves are behaving on the surface of the ocean. Now, at the same time, it's not just weak winds that can smooth out the water. According to an oceanography professor from the University of South Florida, other stuff like freshwater, ship wakes, and even natural ocean movement, such as underwater waves or currents, can change the water's texture too. And all these phenomena can mess with how the sunlight reflects, which, in turn, can cause weird patterns in the images. Some of the darker lines you can see, for example, inside places like Delaware Bay or Chesapeake Bay, might be freshwater mixed with things like algae, dissolved plant material, or even natural oils. But those patches aren't usually as big as the giant dark blob they saw off Delmarva. It happened on May 6, 2023, when the ocean just east of the Delmarva Peninsula was super calm. There was barely any wind. So the surface of the water was all smooth and glassy like a giant mirror, and the angle was just right to make it look dark. Now, even though these sun glint effects make for some stunning satellite pictures, they can be annoying for scientists who are trying to study the color of the ocean or track things like phytoplankton blooms. Basically, sun glint can cover up the stuff they actually want to see. So, to work around that, scientists and engineers have built tools to either fix the data afterward or design sensors that avoid the glare in the first place. For example, the new Ocean Color instrument on NASA's upcoming PACE mission is designed to tilt just enough to dodge the worst of the sun's reflection. Oh, by the way, NASA scientist Ralph Kahn reminds us that our eyes can deceive us, judging brightness based on what's around it. So even a dark patch in an image might actually be pretty bright. It just looks dark compared to the shiny parts nearby. Now, let's tilt our heads back to the night sky. See that weird glowing spiral? Looks pretty extraterrestrial, doesn't it? Well, chances are it was just a SpaceX Falcon 9 rocket doing its thing. When these rockets launch satellites into orbit, they sometimes dump leftover fuel once they're high up in the atmosphere. That fuel freezes and starts spinning around as the rocket moves. It looks like a mini ice tornado in space. But what makes it look even crazier is sunlight. Even if it's dark where you are, The rocket's way up high where the sun can still hit it. The light reflects off the icy fuel spiral, making it glow. Just a bit of night sky drama, but nothing mysterious. Now, let's admit it, you aren't likely to see a real-life flying saucer. What you can see, though, is a lenticular cloud, which looks pretty much the same if you ask me. These clouds pop up high in the sky, usually around mountains, where moist air flows over them just right. Even though the wind is moving super fast, these clouds just kind of hang there, totally still, like someone has parked them there. They're usually perfectly shaped, smooth, and saucer-like. And still, it's just nature showing off again.
3, 2, 1.
Another kind of weird stuff you might see in the sky is space junk. When satellites stop working, a lot of them are just left behind, floating around. Eventually, they slow down because of atmospheric drag and start falling back to Earth. When they do, they light up the sky like massive fireballs. Sometimes it can last for nearly a minute. As the pieces burn up, the different materials they contain can create colorful streaks in the sky. And once in a while, chunks actually survive the trip and crash land on Earth. The leftover bits are often twisted and scorched, and they look so strange that people sometimes think they're wreckage of spaceships from another planet. But nope, just another piece of our own space clutter coming home. Now, look at this. A plane is flying straight toward the horizon and leaving behind a long contrail. You know, that artificial cloud from engine exhaust? And in some cases, it can look like something is falling from the sky. The wind can blow those trails wider, making the whole picture seem even more dramatic because it looks like smoke from a crashing object. Add in the red glow from a setting sun and, well, it looks like something is on fire and plummeting to Earth. Plus, if sunlight reflects off the bottom of the plane just right, it can look like there's a glowing core in the crashing cloud. But the giveaway is the speed, slow. Real falling objects, especially from space, zip across the sky at thousands of miles per hour. So if it's barely moving, it's probably just a plane. Nothing to worry about. Wink wink.
On January 26, 1700, one of the biggest earthquakes in history hit off the coast of the United States. It had a magnitude of 9, which puts it in the top 10 most powerful earthquakes ever recorded. This earthquake triggered a huge tsunami and changed the coastline all the way from southern British Columbia down to northern California forever. Back then, the area wasn't very populated, but thanks to some clever research, scientists figured out exactly what happened that day by looking at old geological records, tree rings, and even some history from Japan. On the same day as the earthquake, a massive tsunami also hit Japan's eastern coast. For a long time, no one connected the two, but in the 1980s and 90s, researchers realized the tsunami in Japan had been caused by the earthquake in the Pacific Northwest. They were also able to pinpoint the exact day, January 26, 1700. They even found old trees in coastal Washington that had all perished around the winter of 1700, which matched up perfectly with the timing of the earthquake. The earthquake came from the Cascadia subduction zone, a fault where the Juan de Fuca plate slides under the North American plate. This fault stretches about 700 miles, from northern Vancouver Island in British Columbia to Cape Mendocino in California. The pressure from the moving plates builds up over time, and eventually, another big, devastating earthquake will hit the same region. It's just a matter of time. By looking at the geological records, past tsunami deposits, and signs of land level changes, scientists can figure out how often these huge earthquakes happen. Emergency planners have been preparing for the next big quake, often calling it the big one. Scientists believe earthquakes in the Cascadia subduction zone happen every 200 to 1,000 years. And since the last major one was over 300 years ago, the Pacific Northwest is definitely due for another. When it happens, the earthquake is expected to be as big as the one from 1700. But this time, it'll affect around 15 million people. The devastation will be severe. Buildings will collapse, roads and runways will crack, and bridges will fall. Communication in and out of the area will be cut off. But the worst part? The earthquake will trigger a massive tsunami that might hit parts of the Washington coast in as little as 10 minutes. It's not a matter of if, but when the Cascadia subduction zone will break. When it happens, it will be the worst disaster the US has ever faced. Worse than the Hurricane Katrina or Superstorm Sandy. It'll impact an enormous area stretching from southern British Columbia all the way down through Oregon to northern California. That means millions and millions of people will be affected. Fairchild is considered a backup staging area for handling the aftermath of the earthquake, with Grant County International Airport in Moses Lake being the main one. For those who will survive the initial quake and tsunami, the aftermath could be just as disastrous. Aftershocks will follow, and transportation will be a mess. Roads will be damaged or completely blocked, airports will shut down, and most of the main routes, like Interstate 5, will have bridges destroyed. This means food and water supplies will be cut off, and it will be incredibly difficult for help to get in or for people to escape. Gas pipelines will most likely be damaged too, and restoring them could take anywhere from a few days inland to weeks or even months along the coast. Power outages will be widespread within 100 miles of the coast throughout the entire Pacific Northwest. And water could be out for 3 to 7 months. Even telecommunications will be down for 2 to 3 months across the Pacific Northwest, Alaska, and even parts of East Asia. The good news for eastern Washington is that it will mostly avoid the worst of it, thanks to natural barriers between the west and east sides of the state. The tsunami may hit the Columbia River Gorge, but it will lose energy quickly because of a sandbar under the river. The Cascade Mountains will absorb much of the earthquake's impact, so the east side won't feel it as strongly. And since eastern Washington won't get hit as hard, it'll be up to them to handle the aftermath of the quake. That means helping western Washington, taking in refugees from the areas that got destroyed, and delivering supplies to where they're needed. Scientists have looked at other major 8.0 to 9.0 magnitude earthquakes like the ones in Chile in 1960, Alaska in 1964, and Sumatra in 2004, and Japan in 2011. These kinds of quakes can shake the ground for anywhere between 6 to 10 minutes, and that's a long time for the ground to be shaking. Such quakes are super intense because they happen close to Earth's surface, so it's not just a quick shake. It's a long, strong one that can cause a lot of damage. If the Cascadia earthquake and tsunami were to hit tomorrow, over 13,800 people could lose their lives, and about 107,000 people could be injured. The economic toll in Washington, Oregon, and California could top $70 billion. To put that into perspective, we can compare these numbers with some other major earthquakes. In Chile's 1960 earthquake, about 1,650 people lost their lives. The 1964 Alaska quake resulted in around 140 lives lost. The 2004 Sumatra earthquake and tsunami took the lives of an estimated 280,000 people. And the 2011 Japan earthquake and tsunami caused over 20,000 casualties. Authorities know about the dangers of the Cascadia fault, but even with all the planning, no one can say for sure what will be needed when the big quake hits. Right after the earthquake and tsunami, the areas outside the immediate disaster zone won't be able to help much because roads and airports will be destroyed, and resources will be limited. How can we deal with this kind of disaster and its effects? We don't have all the answers yet. Right now, let's focus on the Cascadia subduction zone. It's a huge fault line that stretches about 620 miles from Vancouver Island to Cape Mendocino in California, sitting about 93 miles off the coast. It's like one tectonic plate is slowly sliding under another. When the plates are close to the surface, about 18 miles deep or less, they get stuck because of friction, kind of like pushing two rocks together. Over time, this creates a lot of pressure. When the pressure finally becomes too much, the plates slip, causing a massive earthquake. This is called a megathrust earthquake, and it can be huge. Below the area where the plates are stuck, there's a zone where the plates move really slowly. We're talking about just a few inches every few months. This slow movement helps to release some of the pressure, but it also builds up more pressure on the parts of the fault that are still stuck. This means that over time, it increases the chances of a huge earthquake happening. These massive quakes, called Great Subduction Zone earthquakes, can be stronger than magnitude 8.5. Megathrust earthquakes are the biggest earthquakes that happen. They can go over a magnitude of 9.0, which is insanely powerful. Just to put it in perspective, a magnitude 9.0 earthquake releases 1,000 times more energy than a 7.0 and 1,000,000 times more energy than a 5.0. These earthquakes happen when a lot of pressure builds up in a part of the fault that's locked, which means the plate can't move past each other. When that pressure gets too high, the fault finally ruptures, releasing all that built-up energy in one massive shake. The Cascadia subduction zone is super long. That's why if it were to rupture all at once, it could produce a large earthquake. Scientists have studied this region and found that about 18 miles below the surface, the fault is completely locked. The plates there aren't sliding past each other. But deeper down, the plates start to slide more smoothly, causing less friction. This is important because it tells us how much stress is building up in that locked zone, and how it could eventually lead to a major earthquake.